Okay, so it's Sunday at 8 o'clock on the 11th of December. So what we did on the screen there is we just went over the different degrees of freedom for if you have a basically, if you have this piston here where that's actually now a member, and it ended up having, that's a prismatic slider, so there were 4 different F1 joints. So we had the slider one that's 4, then we had 1, 2, 3 different pins, and we had 1, 2, 3, and then the ground link was 4. So we had 4 links, and we also ended up with 4 of these F1, so we end up with 9 minus 8. And then if you look at the second one where it was just right in here, so right, that allows 2 degrees of freedom. So basically we had 3 links because we had 1 here, in the ground, so that's going to give you 3. And then for the F1s, we had 1, 2, 2 pins, and then this one down here is an F2, so that's where that one came in. So we also had 1 degree of freedom. Okay, some more questions.
Do you think you can go over one where it has like an angled rotation, and then you have to make that assumption of like omega cross r equals 0 or something like that, that additional equation?
Yeah, so there was one of those that was on the did you see the review problems? Is that what you're talking about?
Yeah, I'm looking at it right now.
Okay,
It's like
so,
15.2.
yeah, let me go look through it. Hold on a second. Maybe I can just bring that one up and we can talk about it. So I might be able to share my screen with just that one if I can find. Sorry, let me see here. Oh, there it is. Okay, so yeah, let me open this guy up. So okay, is that showing up on your screen now?
Oh, it just went away.
God, I don't like this thing very much. Let me see here. Did it pause share? So what do you see? So what do you guys see on your screen right now? Anything? Okay, wait. Let me see now.
There it is.
Okay. So let me zoom up a little bit, right? So this is just one where, you know, in the end, it's actually not too bad at all, because all you have to do is start out and you say, well, the velocity of A equals velocity of B, just like the stuff we've done before, right? And in this case now, it's going to have 3 different components, right? But the thing we know is the direction how VA and VB are both going, right? We know which direction VA, it's just constrained in the Y direction. Is that okay?
Yeah.
And then for this one here, right, when you're going to do the VB one, that's also constrained, right? Because it's got to go up and down on that slot. Right? So the key is to first make out those key ones, right? So now we're gonna do right here, and we say, well, velocity of B equals velocity of A plus omega cross R, right? So then you just have to figure out, all right, which direction is B? So you set up and make your unit vector, but kind of like back what we used to do in statics. So you know, you can do sines and cosines, or you can go through and just figure out the overall length there. Okay, so that's what we were doing right here. This might even be one, I don't know if there's homework or something, one we might have done in class. Okay, is that all right so far then?
Yes.
Okay, so velocity B, like you can see here, that's where I was saying that's constrained to go along the slot. So I'm going to scroll up a little bit, right? So that's just how it was moving back and forth in this area right there, right? Then you know velocity of A, like I was saying before, is also constrained just to go up. Okay? And then the final thing is we've got this R of B with respect to A. right? So then you just have to figure out, all right, what's my vector that's going from A to B? So if you look again back up at the figure here, right, from A to B, so here's your X direction, right, your Z direction, and your Y direction. Does all that make okay sense to you?
Yeah, but how come when you're defining dV, you have that 20, which I'm assuming is a magnitude, but
Yes.
then you have 0.8 inches, or why is it 0.8? And I don't think those are the right units with the diagram, because we have like a 9 and a 12 here. Like, where's the 0.8 and 0.6 come from?
Right. So then you do, you have to figure out, well, what's the total length there, right? So it ends up being, I think on that, it ends up being like a 9, 12, 15 triangle, right? So you have to do you have to figure out what the unit vectors are, right? So you have 9 over 15 is the component that's going in the Y direction, right? And then 12 over 15 is how it's going in the, I think I did that right. Right, is how it's going in the X direction.
Yeah, how come it's not just like 9 in the Y and 12 in the X?
Well, because you could also do it like just a cosine and a sine, right? So if you know that something's going 20 meters in this direction, right, then how much of it's in the X and how much of it's in the Y, right?
Yeah, okay.
So that's just another way of doing it, right? It's like a 3, 4, 5 triangle, or in here like this. That's the 20, and then although it's skewed a little bit, but then you have like this would be, and I don't think I have the X, Y's. Oh, actually, I might even. It's essentially like this, where that's 9 and that's 12. So then, to figure out how much of it you do this, you just have to do the triangle.
Right.
Okay. So, and again, you could have done that with sines and cosines. You could have figured out what the theta was.
Mm-hmm.
So then, is this part okay for you? This one right here should be fairly straightforward. You're just finding out the R vector, right? And you're doing omega cross R.
Right.
And then
that's fine.
Okay. And then you could have any of those components for these. You could have an X, a Y, and a Z.
Correct.
All right. So basically then you're going to end up with, you don't know what omega X or omega Y or omega Z is, and we also don't know what VA is. So that means we have 4 unknowns, but we only have 3 equations, an I hat, a J hat, and a K hat, right? So X, Y, and Z components. So what that means we're going to have to do is find one other relationship. And what will happen is when we look at the, I'm going to scroll back up to the figure here. For that thing to actually have some sort of a, basically for this guy here, I don't know if you can see that, hold on. For this one, for you to have for A to have a velocity with respect to B, it really wouldn't do anything if it was just kind of spinning around, on that axis there. So basically, our last thing is we say that, well, omega doesn't have any components along that axis between A and B. So basically, our last thing is that omega dotted into, sorry, sometimes it doesn't write as well, that's going to equal 0. Okay, and that's
right.
That just doesn't do it. It doesn't make any sense if I had omega that's along that component. So that actually gives us our 4th equation. So that would be, I'm scrolling down now. That's what we're saying by this constraint right here. Is it saying that none of that's going to be in the none of that omega is going to be along that axis. So then when we do the dot product, it gives us this relationship. We have 4 equations, 4 unknowns. So, and we would probably just ask you to set that up and not have to solve it.
Perfect.
Okay, good. How about Ethan, Megan, Spencer, Val? You guys got a question? All right. Is anybody typing? I'll give you another second to type one, and then we'll go back to Aaron, see if he's got more. Can you guys all hear me? All right, Aaron, you got another one?
Yeah, going on to I forgot, like, I didn't know that you had posted the solutions to these, but I mean, it makes more sense when you go over them anyway.
Sure.
If you talk about this 15228, the one that talks about the spraying of paint on like the thumb thing.
Okay, that's
the one after.
That's down from here, right? Okay, right here.
Yeah.
Okay. Yeah. So, did you have a specific question of it yet, or not?
Yeah, like the geometry stuff is what usually like gets me. Getting like exactly what, like the R's and stuff, like the velocity. Not only the R's, but like the relative terms.
Okay. Well, so if you look at say this one, I'm going to zoom it up a little bit more so that, because I think it's probably not great to for everybody to see. Right. So basically, looking at this thing, you always want to look for points that might kind of help me out. So things that I may know something about, because if we look here, right, we're just asking for velocities and acceleration. So there's a couple different points that I could look for, right? But at this time, right, then really, there's A's not having a velocity, point B doesn't have a velocity, right? C doesn't have a velocity, right? So I can kind of choose, a number of these different things that I might want to, right? But I might even, what's another point I might choose to kind of reference?
Can you do F?
Yeah, I would probably look at point F, right? Because it's the center of that thing there, right? Even though it's not on that rigid body, it's still not a bad, it's a pretty decent point to kind of end up choosing, right? Especially since nothing else is going on there. F is okay to use. Okay, so
would it be there's like no acceleration of F either, or if you were to ask for acceleration? Or
well, we do.
Yeah,
we do ask for acceleration there. Okay, so now what you've got to do is think about, all right, well, I've got that U part. So does it make sense to you that first of all, the point D is going to have some sort of an acceleration due to that omega 1?
Yes.
Okay, so that so first of all, and it's going to have a a velocity as well. Do you have a guess for which direction? Say, what's the velocity of just point D? If I don't have the U, then what would the velocity of point D be in?
If you don't have the U, the velocity is going to be toward the Z.
Yeah. Okay. So, you can a lot of times you can kind of think of it, it gets a little bit hard sometimes when you also bump in the Coriolis, but essentially you're going to have that, the part of D, and then, the next part to think of it, because you're setting basically a rotating frame going around with the omega 1. And then with respect to that frame, does that part, right, that the paint that's right at that point in the paint, in the pipe, does that little part have its own velocity? You know what I mean? So like if you're sitting at C, yeah, it's got that one with the U, right? Does that make the right sense?
Yeah.
Okay, so I'm going to scroll down some now, right? And you can sort of see that's.
My issue is like picking it like an axis and then working from that axis. Would we pick our axis at B, the one that's given, or would we want to make it axes like at F or something like that?
I mean, you can do B, because it's not going to, right, when you do like an omega cross, it's not going to have any effect, right? Because B to here, right, that doesn't do anything, right? Because it's omega cross of an X one, and then if I go all the way down to to F there too, so in effect it doesn't really matter that much.
Right.
You know what I mean? So if you just have to pick your good reference point, and then you just go from there.
Okay.
So you could do it from B or you could do it from C, and I actually don't even, or you can do it from F, and I don't remember which one we went to. It looks like here she chose to do B, right? So, but you didn't have to, right? So you could solve your axes at B, but that's got 0 there, and so here's what I was saying before. If you look at this case right here, right, that doesn't come into play at all because I cross I is just 0, right?
Right.
Okay, so
then all you have is the relative term in that case.
Well, no, because you still have this term, right? You still have the J part crossed into this.
Okay.
Right. So the 0.25 times sine 60 is going to basically give you this amount right here, right? And then because remember that thing's just rotating out kind of like towards you right now. So that's where that 0.25 sine 60 is going to come into play. And like you told me, I cross J is going to give you plus K. So this term right here crossed into this term right here gives you one of the velocity ones, right? And then this term right here, which is your U part, which is your VREL or your R dot, that gives you the second part of the velocity of D.
So when you're talking about the R dot term, the relative velocity, that 0.15 came from the given, right? So that's the U.
Yes.
Constant U. And then the parentheses part is just the vector term, right?
Yeah, that's just this guy right here, right? That whatever your capital omega was, which was the 0.4 in the I hat, and then crossed into that R vector that you've chosen.
Okay. And if that formula was to be used against VF, VF would also be 0, right?
Yeah. Yeah.
But then what would be omega? Omega wouldn't be the omega 1, would it? Because F1 is not on that same shaft.
It doesn't have to be actually on it. Your axes can kind of be wherever. You just set how it's rotating, right? So you can always say that I've got a set of axes, fixed at point F, and it's rotating around with omega 1.
Oh, okay. And then your R, it would be B to F, would just be like basically. Oh, I see. So just have to change the axes that you're referencing.
Yeah, you would just then have the instead of the 0.45, that part wouldn't be there.
Be cosine. It would actually be sine minus sine of 250-ish, something like that.
I'm sorry, sine of 0.25.
Yeah.
Yes.
Cosine. Yeah. Minus for the I, and then a positive cosine something for the J.
Yeah.
You're doing it about it. Okay.
Still have that. The I's still don't matter because I cross I is 0. So the only thing that comes into play is that 25 sine 60 in the J hat.
Okay.
Okay. And
that
then
makes sense.
Ethan had a question too about he's got a question on the diagrams there, right? So in something like this, I mean, it always helps for you to visualize there. So the things I would definitely want you to have to do is make sure that they're axes that are defined, how they're rotating, and then you definitely have to tell me, capital omega equals for I, right? You have to define exactly what that's going to be. It wouldn't be bad for you to write, 3D kinematics on there, so it shows me the exact dynamics principle, but that won't be any points. But that can also, maybe help you with your thought process there, Ethan. Does that make sense to you, Ethan, then? Okay. Were there any other questions about this particular one?
Was there acceleration in the solutions done about this point D as well?
Yeah, I think that's what we did for there.
Oh my God. Right.
Right. But it's all the same type of thing, right? The critical things are right here. right? And then so in fact, we just kind of put, whatever the I is, because we don't care, because it's gonna cancel out, right? And then this is that same kind of term that ends up being important. And then if you remember, we've had a couple different times where, since it's going in a curved path, you end up with this rel term right here. Remember, it's like a v squared over rho. So we had one of those on the on exam 1. We had several homework type of things for it as well. So you just have to be careful that you realize that, hey, this is also an a rel or kind of r double dot term, because I'm going in a curved path.
And what term is that in again?
That would be an a rel term.
So the r double dot?
Yes.
And that's over rho?
Uh-huh.
Which is the distance from the center to the point?
Yeah. What if I'm in a car going around a curve, right? What's my linear acceleration?
Inward.
Yeah, and that amount is, equal to
V squared over r.
Yeah, well, that's exactly what that is, right?
Yeah.
That's what this guy is right here.
Okay.
Right.
If you were to do it about f, then it would be just normal and the tangential, right? Oh, but the Coriolis is due to the relative term.
Right. So it'd be the same exact thing. The only difference with doing it with the f, Aaron, is what your r term is. And like we said before, doesn't matter, because everything ends up being kind of an I cross I, so it doesn't really matter in this case.
Okay, I got it.
Okay. So Megan's asking, yeah, it's exactly what that is, right? Is a normal type of term, and then if it was speeding up, it would be, like a u dot. And we've had quite a few types of problems like that we did for either homework or that we worked in class as well. So yeah, that r dot xyz is basically the u term that was there. Okay, so then you had another question, Megan. You're saying from lesson 5. Let me see what I have there. Let's see. So that was a plate linkage solution. Okay, so let me see if I can get into the share thing again. Get rid of there, and then let me see about, shoot, where did that go? Okay, so I'm going to try to do a new screen share. And okay, can you see that question you had up there? Okay. So it did have, Megan, so it did have both an I and a J component, right? There was a cosine and a sine term there, I think, with it, right? Let me see here. Right, so you had both a sine and a cosine right there, so it did go both in the I and the J. And that is what's towards 0.0. Okay, so can you see the plate question that she was asking about before? Okay, so that's up. So I'm going to zoom in a little bit more. So, this one's not really that too much different than that problem we had on the on test one. Okay, so for all of these, what you want to do is first, what's kind of the point that connects these two, right? We have two rigid bodies, so what's the point that really connects the two of them together? Yeah, it's point B. So that's going to be your critical point there. So what you want to do then is write the velocity of B, right? And you want to start that off, and you can do it with respect to O first, and then you do it with respect to C, and then you set them equal to each other. Okay, so that's your basic process that you do for all of these kind of linkage ones. I mean, you can also go, do velocity of B equals velocity of C plus omega cross R plus V rel, and then you can go velocity of B equals velocity O plus omega cross R plus a V rel, right? So you can kind of, you get to decide which way you go. But a lot of times I like to go to whatever that central point is, especially if I just have two bodies there. And that's kind of fairly typical to just have two of them, because you have a single degree of freedom when you have that, and a slot or something, a slot or a collar or a hydraulic actuator type of thing. Those are really the three main rel ones that we've got. Okay. So, Megan, was there a particular part in this that you didn't quite get? Yeah, okay. Well, actually, that sets it up perfectly, because it's essentially almost the exact same thing that we just did on that paint one. Okay, so let me just show you here real quickly, because we've got just the overall. See, I should be able to do a pen here. Let's do it in B, right? So what I just said is basically what we did, right? So we did velocity of B with respect to point C, realizing the velocity of C is 0, right? So that one should be pretty straightforward, hopefully. And then when we get the second one here, right, is what we did. Velocity of B is equal to however the plate is rotating, right, whatever omega that thing has, and then we're going to do it crossed into the vector that goes from point O to point B, right? We set those two equal, and then we can have basically two unknowns. Okay, so does that part seem okay to everybody? For just
and what direction is V rel? In the positive J?
Yeah, that's what I guessed, right? So it's got to be constrained in the slot. So at that instant in time, then the VB rel's got to be tangent, right? So if this, wherever I am on that curve, right? So if I was way up here, then the VB rel would have to be like in that direction, right? Mm-hmm. So the velocity's got, if I'm going in a circular path, right, then it's got the velocity is tangent to that path. Okay. So in this case, we didn't know what omega AB was, but we had the omega BC, so we can now go through to solve it, right? That the omega BC was given as 2 radians per second, and it was going counterclockwise. Okay, so omega BC, right, was going with 2 radians per second, and it was constant. Okay, so that was omega, and then alpha was equal to 0. And that's for BC, right? And then we had to find AB, and we had to find V rel, right? So we always have, with the velocity ones, we can have up to 2 unknowns because we have X and Y. All right, so now we've got to take those, and we're going to figure out, well, what's my accelerations, right? And essentially, we're doing the same thing all over again. So we're first finding the acceleration of B with respect to point C, and we just said that, hey, this acceleration is 0 because the omega BC was a constant. Right, so that part's just kind of a plug and chug, and it should make sense to you that this thing is going in the plus I and the minus J. And I'm going to scroll up here, right? Because which way is that normal, right? The normal acceleration of B is going to point back down in that direction. That's plus I and minus J. Okay? So that part's just like what we've done before in a lot of things, right? And now we're coming back here to the full equation, which is the harder one, right? When we start talking about the acceleration of B with respect to point O. So the first part's if you look for each of these, I'm going to hold off on this one first because that's the hardest one, and that's the one I think Megan wants the help on. So the first is just that omega is just whatever we found up above, right? That's how that plate is rotating, and then this Coriolis term is due to this 200J here. So we've got that that VREL in a rotating frame, so we end up with that Coriolis term. Then the second is, you can also think of this a little bit like these two terms here are kind of like, well, what is the velocity, or I'm sorry, what is the acceleration of a point that's on the plate that's like right beside point B? So what I mean is, like right here on the plate, there's a point right beside where B is, moving up and down that slot. So that's really what the omega cross R and alpha cross R will give you in this time frame. Okay, and that's just from doing your omega cross R and your omega dot cross R, and that's what the angular velocity and angular acceleration of the plate are going to be. Okay, then a little bit harder part is really related to what we were just talking about. So let's say that I'm a car going around a curve, right? Then which direction would my tangential acceleration be in? Megan, what direction? Yeah, Megan, which direction could my tangential acceleration be in? Yeah, it's constrained to the j hat, and I can guess either way. I can guess either a plus or a minus, right? But it's going to be tangent in this direction, right? So let's just guess that the a rel, and I can just call it if I want a rel tan, right? Whatever you want to call it's fine, right? But I'm going in a curved path, right? So if I'm going in a curved path, what other type of acceleration do I have, Jason? Yeah, I've got a normal one, right? So that's going to point in towards the left. Okay, so that's going to be like my A rel, right, normal. Okay? So do you see how this is this is nice because it ties directly into what we were just talking about before. So then if I go down, right, to this point here, that's what I had, is just what you guys are saying, where this is the tangential part. So that's why we had like an A rel and the J, and that's how much that point B is kind of speeding up in the slot at that specific moment in time. And then this second part here is going to be what our VB squared rel is, right? So that's how that thing's moving up. It was like the U, which was the velocity for the paint thing, right? Same type of thing. So V squared over rho. In that case, the radius was 40. Okay. Anything else there, Megan? I see you say you got it. Was there any other questions on it? Great. All right, more questions. First, we'll give everybody a chance who hadn't had one, didn't ask one yet, and then we'll go back and see if either Megan or Aaron has another one. Okay, let's see, 15244. Yeah, so let me see which one that is. So we've got, how far down was it? Oh, this is the plate one that's kind of rotating around. Okay, I see it. Okay, so let me stop that share. And okay, so can you see this? Is that screen up now, Jason? Okay, so in this case, right, we've got a what's happening is you've got two different rotations going on, right? So there's always a couple different ways, of course, you can solve these. If I was looking at it, right, as we're going through, I would say we've got one axis that's sitting like this, right, and then we've got another one that's rotated around. And depending on if I want to attach it at A or if I want to attach it back down here to O, it's kind of however you want to do it, right? Because we're always talking about the directions, and then it's my R vectors that really make things happen, right? That's how stuff depends. So if I was working with, I think we might have a little bit different solution on there, but then you could say, all right, I've got this thing is rotated around where like that's a Y prime, then that's the, hold on a second, then that's a Z prime, and then X prime is still basically coming out the side. Okay, so that would be like an X prime. This one, since we rotated everything around, then that would be like a Z prime, and then that would be like a Y prime. Okay, does that make right sense? Okay, so you can either then start going through your rotation matrices, however you want to go, but let's say that we're going through here. So basically, omega, if I do for the whole thing, right, then omega would be omega 1 y, right? And then what direction is this second one in? Yeah, so it's got y and z, but I could also do it in like a y prime, right? Okay. All right, and you wanted to go over part A. Yeah, when it's just 0. So is that when it looks like that's when it's down below, right, at the end. Okay, so then if I was, how I usually like to solve these is actually I would go to point A. So I would tend to do like velocity of B is going to equal velocity A, right, then plus my omega cross R from, sorry, hold on, I gotta figure out what I do with, it's not quite as good to do this writing with the inking on, and Adobe isn't quite so good. Hold on.
How are you solving velocity?
Excuse me?
Why were you solving for velocity there?
We can do, yeah. So I guess because it's the same basic thing, I didn't look. So yeah, we can do acceleration. Sorry. So acceleration of B equals acceleration of A plus you can do your omega cross R, right? And that's going to be B with respect to A. And then you've got your plus omega cross R of B with respect to A, right? And that's your dot. Okay. So now, like what you were saying before, Jason, is we could also then do this where we say that's omega 1 y, but now we want to put that that y prime into our other axes, right? So how could we write that in terms of the the y and the z, right? Because now what we have is the x, y, z, and it's rotating around with omega 1, and then we can have the x prime, y prime, z prime there is one that's now rotated around but still going, and then we could also do another one like a u one that's attached to the bar AB. Okay, so then what is omega 2 going to be in terms of? Yeah, so you can do that around the x, okay? But sometimes, if I'm not doing a full vector, since I'm just doing that, yeah, I can just do sines and cosines, right? Because that's all the, that's all the transformation matrix is doing. Okay, so that omega 2, and I think we probably did that down below, right? So if you look at how the she decided to go through and Oh, she might have done it all in the prime one instead of doing it in the,
And then converted to XYZ.
Yeah, so you could go through either way, right? So it looks like, so this was Professor Rossman's one that she worked out. So she decided to do it.
Omega 1. But wouldn't you have to convert omega 1 then to Y prime, D prime, and X prime?
Oh, no, I'm sorry. She left the omega 2, like what I was doing. Sorry. So she just put it into components right here. Right, so that's the omega 2. So she did like what I was just starting to do. Okay. Does that part make all right sense to you so far, Jason? Did you already write yes, or was that an old yes?
Is 0.866 cosine 30?
Yes.
Mm.
And then 0.5 is sine. Okay, and there could be one in there as well. So, what I tend to do a little bit more, so she decided to go from point O, but like I was saying, I usually would go to point A first, okay, because then I think it's not too hard to do the A, because when you do the acceleration of A, you end up with that's just going to be omega 1 crossed into omega 1 crossed into R of A with respect to O, right? And that's just going to give you a normal acceleration in towards that way. Okay, well, how did you set your capital omega?
That's the thing.
Okay, so if you did with both, then you shouldn't have had any rel term. Okay, so let me go down and see then, because then it should be, did she not set it equal to both to solve it ever? Oh, so that's where she just didn't go through. Well, let's keep looking then. So you would have, the one thing that you have now is you do have, of course, you're going to have to figure out which you do have a capital omega dot, right? Does that make sense, Jason? Okay, so then you've got the omega 1, which was in, so that was in the Y, wasn't it?
Mm-hmm.
And then you had omega 2, and was that 8.66, which was that in the Y as well? I'm sorry, 0.866. Gosh.
0.866 in the Y and 0.5 in the K.
Okay, so we've got this one here, right? Is that what you did, Jason? Okay, so then you've got an omega 1 times omega 2 times 0.5, and that's going to be in the I hat. Did you get that for your? Oh, okay. And then you're going to take that, right, and then you cross that into that same R vector, which should have just been from, sorry, let me drag that up. Right, is going to be from A to B. So then that's going to be, let's see, what is going to be a minus in the J hat and plus in the K hat. Yep. So you can have like an R cosine 30 in the K hat, and an a minus R sine 30 in the J hat. Is that what you use, Jason? Okay, great. And can you tell us what you did wrong? Was it just a minus sign there in the R? Okay, great. Okay, more questions. Yeah, in fact, that's what we'll probably have them do next quarter. So yeah, you'd have to set up your systems, and then I would do just a transformation matrix in there. So yeah, I mean that's the end part. I think I really like doing a 3D simulation during the labs, just because otherwise it's we just kind of look at things a little bit like here and there. So you use transformation matrices. You then sort of either like what I've done is given you the omega, said like a motor's driving different things with a certain omega, and then if you know the starting ones, and you have to integrate to figure out what all your thetas are, and then you differentiate to get your local alphas essentially. And it gets a little bit hairy in there as you go, but really once you set it up, it's not too bad. So you just have to keep track of all your terms really carefully.
When you're finding angular momentum, do they ask for the dynamic load, say at a bearing, like kind of like the exam? I was kind of confused when you're like, I know you have to neglect the masses. That's what you say, but necessarily, why are we just solving for H capital H dot in essence, or what are we doing when we're doing like the dynamic?
Well, you're just solving it without including the weight. So usually, especially in when you have stuff spinning really fast, that those amounts are typically much higher than just the static loads. Although we did if you looked at the solution for that boat one, in that case the static loads were actually quite a bit higher than the dynamic one. So what you typically will do is you figure out what your dynamic loads are going to be, and then you compare those to what your static loads are and decide which one's gonna sort of dominate and how you would add those together. So when we ask for dynamic loads, and all you have to do is figure out what the reactions are due to your total H dot, right? So that's H dot local plus omega cross H plus R cross MA.
Okay, so you're just solving for that entire H dot, right?
Yeah, that's basic. Yeah, it's just like in the end, it's really just like sum of moments equals I alpha, where I and T, because I alpha is H dot.
So your answer would be sum of the moments at a certain point equals a value, question mark, right? I mean, that's kind of what dynamic loading is asking for.
Yeah, so instead of it being equal to 0, it's equal to 22 in the I hat minus 74 in the J hat, and then yeah. If you were solving this problem that we're looking at on the screen, then basically you would end up doing you would end up solving moments at point O, and you would really just have to put all of your different components up. So I'd put all 6 things up if this was one. So I would have to ask you if I was solving things at O, if I was solving things at point A. If this were, say, a problem on the exam, most of the time we've been doing things more like with bearings as it would go on. So if I was solving this, then Jason, right, you're talking about doing this one right here, then I would be putting, this would be my my setup, and I would end up doing, like basically having both things in all directions. So I would have, basically I'd have a force, I would call it O, Z. Sorry, I can't write all those things because the Adobe screenwriter thing's not very good, but essentially you would have all of the different forces and all the different moments, right? And that's opposed to what a lot of the problems we've done where we've had like a bearing, right? And if a bearing's on there, then we just replace it with, sort of the transverse loads. Yeah, so we'd have like a force going this way and a force going that way. Okay. And then you guys took care of Megan for there. So good. Yeah, there's always a cosine one. That's just that's the same when you do those transformation ones, matrices. Okay, more questions.
When would you use, when you're finding the product of inertia, like the test? Those were easy to find because you had the difference of length, like a difference, like where the location of the center of mass. But when would you use one where you had to use like the integral?
Yeah, I mean, those are going to be if you have some sort of different shape or revolute type of axis. I wouldn't. I mean, I wouldn't ask you for one of those with intervals on the test. I mean, we want you to know where those things come from, but kind of like I told you before, you're either going to use composite type of bodies as you're modeling different shapes as a cylinder or a slender rod or whatever, or you're going to model it in AutoCAD or SolidWorks, and you're going to just find out what those values are. So I'm not going to ask you to do an integral of one on the final exam.
Okay. The answer is 42, right? For all of them?
Exactly. 0.4. 3 significant digits. Okay. I was expecting this is the smallest crowd we've had, really. I was expecting 40 people all on asking final exam type questions.
That's why you should, give us a hint.
I recorded it all, so. All right. Good luck to you too, Jason. Good luck on your other finals too. Okay. So you guys feeling all right about stuff now?
Yeah, not bad. When you mean, for example, for a lesson, when we're talking about the gyroscopes, last one here, we were talking about the gyroscopes, and there was a problem all the way in the back with that fan, where it had like a kind of like a counterbalance. What is that like? How do you calculate that distance? Or are you going to be giving us like a distance of A, and the gyration? That's about the fan, right? That's where it's spinning.
Yeah, so it's like the radius of gyration. That one would be for the spinning part of the fan, right? So you're talking about that problem we worked in class. It's got and I think I posted that full solution too, right?
Oh, I don't know. I didn't.
Yeah.
I should do that.
Yeah, so I'm pretty sure I posted that full. I may not have, though. We might have just worked it on the thing, but I thought I had done that. But yeah, so that's just going to be, your radius of gyration is always for the part that's moving and spinning, right? So that's going to be for the fan part. And so basically, in that thing, you just had to figure out, and that was when we had the static as well when it started out. But pretty much what it was doing is it had like a it was going to process, and I don't remember the exact directions of how stuff went, but it was spinning this way and processing that way. And to be able to do that, you have to apply a moment. right? So
Right.
basically, if it's, let's say it was like this, where the X is coming out, the Y's there, and the Z's there, then if you wanted it to, and let's call this N and that P, then basically the N would be going in the Z direction, and then if you're crossing that, the P direction was about the Y. Yeah, gosh, this thing.
It's I.
Yeah, and then you're gonna multiply that, right? It's also, you had the I in there, which you got from the radius of gyration. So that's going to be then I times N times P, right? And that's going to be in the
Minus I.
Okay, so
And that's the moment in which we have to apply to keep that balance.
correct.
And then the moment that the fan is applying on that weight would be the positive I. The equal and opposite, right?
Yeah, that would be applying to kind of this whole thing right there. Yeah.
Yeah.
Yep. So then in this case, if you wanted, remember it had sort of a static balance. So in this case, and I think it was the other, maybe the P was going the other way. I don't remember exactly, like I said, how it's set up. But in this case, the I would be, like you're saying, the -1. So I'd have to move this weight in a little bit from its static position to get it to have that, the moment going that way, right? So that the moment applied to the spinning gyro is going to be in the negative X. Yeah.
Okay. That's good.
Cool. All right. Well, I will. I am around a little bit tomorrow, like I said, from 3 to 4. If you want to come in for office hours, and I will. Once I leave on this, I will post the video from it.
Okay.
All right. Good luck, everybody, on this one and on your other ones.
Thank you.
All right. Have a good night, everybody.
Yeah, you too. Bye-bye.
Bye.